Hi everyone, welcome back to our course manufacturing process. Today we are going to discuss about bulk deformation process. Learning outcome is describe various metal forming process such as rolling, forging, extrusion, etc. and compute their process dynamics and performance. In bulk deformation process, we are going to discuss about metal forming, fundamentals of metal forming. Then in week 2, we will talk about rolling operations, and in week 3, forging operations. So rolling and forging are metal forming operations. Bulk deformation process, or let us start with the fundamentals of metal forming. So in fundamentals of metal forming, we are going to talk about overview of metal forming, material behavior in metal forming, temperature, strain rate sensitivity. What is the meaning of metal forming? Metal forming means changing the shape of a metal workpiece by applying load. Changing the shape of a material through deformation. This process we call it as metal forming process. So large group of manufacturing process in which plastic deformation is used to change the shape of a metal workpiece. The tool usually called as a die. So here you can see here it's a die, and and then after application of stresses or load, whenever the load exceeds the yield strength of the material, the material will deform, and this material will be passed through the die to get a particular shape. For example, production of tubes, production of shafts, production of bars, etc. So here, as you could see here, we have rolling mills, and the material is passed through the rolling mill. As the rollers rotates, the material will get compressed, and the stresses it cross the yield strength of the material. So what happens is material will undergo plastic deformation, and because of that there will be a change in the shape of the material. So this process we call it as metal forming process. So metal forming process can be done in several ways, such as rolling, forging, extrusion, wire drawing. All these are called metal forming processes. So here we are not going to add any mass, or we are not going to remove any mass, but we are going to change the shape by plastic deformation, by applying large load, sufficient load to cross the yield strength of the material, and hence we can change the shape. So material will undergo plastic deformation. For example, here, as you could see, when a ram presses the material, material will undergo plastic deformation. It will cross its yield strength, and it will come out through the die with this particular shape. So this process we call it as metal forming process. So in this chapter we will be studying different metal forming processes such as rolling, forging, etc. Look at that, the various parts of a car which are produced by forming operation. So valves, filters, spark plug, windshield, wheel covers, oil pan. If you see that, compression molded tires, if you see that, most of them, the products, if you see that, many products in a car are made by for forming operation. Now, what are the stresses involved in a metal forming operation? Stresses involved are like compressive stress, tensile stress, or shear stress. So stresses to plastically deform the metal are usually compressive. If you take a rolling, forging, and extrusion, these three are very commonly used metal forming processes. Rolling, forging, and extrusion, they use compressive force to change the shape. But in wire drawing, stretching the metal, they basically use tensile stress to change the shape. So these are basically the processes. However, some forming processes are there, like bending the metal. In bending the metal, bend the metal, we use tensile and compressive force. So here, whenever we bend, there will be a combination of tensile and compressive forces. Still others apply shear stresses. Whenever we cut a metal, there will be shear stresses acting on it. So desirable material properties in metal forming or material forming are low yield strength, high ductility, etc. Low yield strength means only less force is required to reach the yield strength, and hence you can provide the plastic deformation with the help of very small forces. That is the advantage of low yield strength. High ductility means after crossing the yield strength, the material will be ductile. That means less amount of force is required to give more deformation. So ductility increases as temperature is raised. Yield strength decreases when temperature is raised. Hence, temperature is a critical part, as whenever we increase the temperature, we can increase ductility and we can decrease yield strength. That means the forming process will be very easy whenever we raise the temperature. Other factors involve strain rate and friction. These are also factors which are to be considered in metal forming. So basic types of metal forming processes are bulk deformation, sheet metal working, etc. Bulk deformation, we have several types like rolling, forging, extrusion, and wire drawing. Rolling, forging, extrusion use compression, stress, and wire drawing uses tensile. Bending uses both combined compression and tension. And you could see here some operation like cutting, etc. They use shear stress. So bulk deformation means very large, significant deformation takes place in bulk deformation process. We are going to discuss them one by one. So sheet metal work means like bending or etc. That also will be discussed after this. So bulk deformation is significant deformation produced. Because of significant deformation, massive change in the shape. So bulk refers to work parts with a relatively low surface area to volume ratio. So bulk deformation, for bulk deformation is the materials with low surface area to volume. Area by volume ratio is low, then that such kind of operations we call it as bulk deformation. So it refers to work parts relatively low surface area to volume ratios. So area to volume ratio is less, it can be considered as bulk deformation. Starting work shapes include cylindrical billets and rectangular bars. Normally the shapes include billets, cylindrical billets and rectangular bars. These are the inlet, and output can be shafts or tubes or bars, etc. Now, what are the bulk deformation processes? The first process we talk about is rolling. There are rollers, hardened rollers, and the workpiece is fed between the rollers. The rollers are rotating in opposite direction. So this and then when workpiece or material is fed in between the rolls, what happens? The work material will get compressed, will get squeezed, and it crosses its yield strength, and there will be a change of shape produced because of that. This process is called a rolling process. So here we apply a compressive stress. In forging, the material is the workpiece is kept between the two dies. You can see here stationary and movable die, and whenever we apply a force, there will be a compressive stress acting in the material. Material will undergo plastic deformation, crosses yield strength, hence plastic deformation, and material will have a shape of the die, and this process we call it as a forging process. So workpiece gets squeezed and shaped between the opposing dies. Now extrusion means between the dies the material, and when we force the material with the help of a ram, the material will be squeezed, undergo plastic deformation, and will be forced through a small opening called die, and we will get the output part which has the same shape of the die. This process is called the extrusion process, squeezed through a die opening. This is called extrusion. Again, undergoes plastic deformation, and the force should be sufficient enough to cross the yield strength. So extrusion, forging and rolling, we have compressive stress. Then the next process is wire drawing. In wire drawing, we apply a tensile stress from the other end, and material fed from one side, and a tensile tensile stress is force is applied from the other side. So because of the tensile stress, we can produce wires. This process we call it as a wire drawing process. Pulling the wires, this will reduce the diameter, and hence we can produce the wires. Now we go to sheet metal working. In sheet metal working, forming and related operations performed on metal sheets is called sheet metal work. Any operation or any process done in a metal sheet or a strip or a coil, that is called sheet metal working. As I explained before, we have two types of forming operation. One is bulk deformation. Bulk deformation means the deformation will be massive. And second one is sheet metal working. Any operation on the sheet strips and coils, this is called sheet metal working. Normally sheet metal working will have high surface area to volume ratio, whereas in bulk deformation, low surface area to volume ratio of the starting metal. So how we distinguish between bulk deformation and sheet metal is, in bulk deformation, area to volume ratio is low, whereas in sheet metal, area to volume ratio is high. So this is also called press working because presses are used to perform the operation. Some examples are stampings, punch and die, etc. Now you could see here some examples of sheet metal bending here. A punch operates and the metal bends. As you could see here, the metal bends. And whenever the metal bends, there will be a combined effect of tensile and compressive stresses. This operation, we call it as V bending operation. And here it is a sheet metal bending because it is performed on a sheet metal, and initial billet, initial material or raw material will have a high area to volume ratio. The next common method is you can see here deep drawing process. As you could see here, material, there is a punch and a die, and punch forces the material to deform to take the shape of the punch. This is called this is another process which is called a deep drawing process. Now we have a shearing process in here. As you could see here, there is a punch and die. There will be a clearance between the punch and die. As punch descends, what happens? It cuts or shears the workpiece. This process is called shearing process, shearing of metal workpiece. So these are all included in sheet metal working, working on sheet strips and coils, and the input material or raw material will have high area to volume ratio. Now, material behavior in metal forming. If you look at the study of the material stress strain curve of metal, you could see here until you can see here elastic point. You can see stress is directly proportional to strain. So stress is directly proportional to strain until the elastic point. You can see here Young's modulus E is equal to stress divided by strain at any point within elastic limit. So here, this point, the maximum of the limit, we call it as yield strength. So afterwards, so within this point, anytime if you release the force or stress, the material can come back to its original state or shape. But after yield strength, if you apply more stress or tensile stress to the material, what happens is material will undergo plastic deformation. So less amount of stress is required for more deformation. As you could see here, material will undergo plastic deformation. Once you release the stress, the material cannot come back to its original state. That means the material will undergo a plastic deformation. So the plastic deformation of the material takes place after the yield strength. So if you apply a stress in a material above its yield strength, the material will undergo plastic deformation, and by plastic deformation you can change the shape and size of a material. So this process, we call it as metal forming process, and we utilize above the yield strength area, and material will undergo plastic deformation, and then we can change the shape. So within the elastic limit, as I explained before, stress will be directly proportional to strain. There will not be any deformation. The material can come back to its original state, but after that material will undergo plastic deformation. So sigma E is equal to sigma by sigma by epsilon. This is the equation up to elastic limit. Then afterwards, in forming process, it starts above yield strength. This area comes under plastic deformation. The equation can be written as sigma, the stress applied, is equal to K is a constant called strength coefficient time epsilon strain raised to n. N is a constant called strain hardening constant. So K and N are constants. N is strain hardening constant and K is strength coefficient. So flow curve, this is flow curve based on true stress and true strain. So most of the metals at room temperature strength increases when deformed due to strain hardening. You can see here as you increase the stress, the flow stress sigma, the stress which is required to produce a flow in the material, that means plastic deformation, flow stress is equal to strength coefficient times strain raised to n. N is a strain constant called strain hardening exponent. Now, this equation YF is equal to K epsilon raised to N is the equation for instantaneous stress. That means the stress at this point to produce this much stress at this point to produce this much of epsilon. This stress YF, stress at this point, for example, if you take this point, the stress required to produce this much of epsilon is equal to YF equal to K epsilon raised to N, and that is instantaneous stress at a point that is calculated using this equation. But we don't need stress at a point, we need the total stress required to produce a deformation for a material. So that total stress, we call it as average stress required, that you have to integrate between 0 and the final strain. So when you integrate through the curve, flow curve, you will get the average stress, which is K epsilon raised to N divided by 1 plus N. YF is the average stress, K and N are constants, epsilon is the maximum strain during deformation process. So the average stress required to produce a part is equal to, or produce a deformation is equal to K epsilon raised to N by 1 plus N. As I explained, K and N are constants depending on the material, etc. Epsilon is the strain, and 1 divided by 1 plus 1, which comes in denominator. Now, temperature in metal forming. For any metal, K and N in the flow curve depend on temperature. You can see here. So K and N are constant, strength coefficient and N, they depends on the temperature. Both strength K and N are reduced at higher temperature. So as we increase the temperature, when we increase the temperature, K and N will decrease. If K and N decreases, flow stress decreases. As flow stress decreases, it is very easy to deform a material. That is the advantage of temperature in metal forming. As you keep on increasing the temperature, K and N will decrease. As K and N decreases, the required stress will decrease. That means less amount of force is required to deform a material. In addition, ductility also will be increased at higher temperature. That is the advantage of temperature or effect of temperature in metal forming. So any deformation operation can be accomplished with lower forces and power at elevated temperature. This is the main advantage. So any kind of deformation is possible, or large amount of deformation can be possible with a low force and power when we heat the material and do the operation. So temperature, depending on the temperature of the operation, we classify metal forming into 3 categories. They are cold working, warm working, and hot working. So cold working, warm working, and hot working we'll discuss in part 2 of our week 1 material. Now you can see here there is an example here. K, value of K is given, a strength coefficient is given, N is given. During a forming operation, final strain that the metal experience epsilon is given. Determine the flow stress at this strain and the average flow stress that the metal experience during the operation. So the first one, first thing, what we have, what values we have? We have K, we have N, we have strain epsilon. So first step, determine the flow stress at this strain. That means YF, the instantaneous flow stress, is equal to K epsilon raised to N. K is given strength coefficient, epsilon is 0.85, which is the strain, raised to N is a constant value. You can calculate the flow stress or instantaneous flow stress at a point in the flow curve. But also we have to calculate the average flow stress. Average flow stress is equal to K epsilon raised to n divided by 1 plus 1. As you could see here, numerator remains the same, k epsilon raised to n by 1 plus n, 1 plus 0.22, that is 1.22. So 435 megapascal average flow stress is required for this operation. Thank you for listening. Thank you very much.